Okay, we are about to start. Just share the screen. And we need a confirmation if the shared screen is visible to you.
Yes, sir.
Okay, Vikas, thank you very much. And thank you, Junaid, also for showing up in the morning. So last time we finished our discussion on discrete time Markov chains, and we looked at various different views of discrete time Markov chains. Okay. We also looked at the flux flow from each of the state, which is the summation upon pi I Pij, the flux out of the state. And then we looked at the balanced equation view, which is the flux in is the same as flux out. And we also looked at the stationary distribution or the limiting distribution point of view. We also looked at it from the point of view of the stationary probability being the being the reciprocal of the mean return times to a state. Okay, and then finally the time averages, then the amount of time that a Markov chain will spend in a particular state, that is also given by the stationary probability or limiting probability of being in that state. Okay. So two different things. You look at the Markov chain, what is the probability you will find the Markov chain in state J? That's one thing. And in the long run, how much time do you see a Markov chain spending in that state? These two would be equal. These two views will be the same. So today we are going to jump into a more realistic kind of a Markov chain, which is the kind of Markov chains that we can be used to model the real world processes, and that is a continuous time Markov chain, CTMCs, continuous time Markov chains. Okay. So if you recall from the definition of DTMC, discrete time Markov chains, we said three things about that. We said three things about that. One is that transitions occur at discrete times. Okay. Or unit steps. Second thing that we said about the discrete time Markov chain is that past does not matter given the present. It's only the present which matters. Okay. Past does not matter. So the second property is basically because of the Markov property. Okay, Markovian property. And the third is that the transition probabilities are stationary. They are not changing with time. They do not change with time. Okay. So the way of representing the discrete time Markov chain was that probability xn plus 1 is equal to j given xn is equal to I. Okay. Just the previous guy and all of the previous guy. If everything is given, xn minus 1 is equal to small xn minus 1. xn minus 2 is equal to small xn minus 2. dot x1 is equal to small x1 and x0 is equal to small x0. Okay. So I am looking to find the probability of x plus 1 is equal to j given xn minus 1, given xn minus 2, given all of these x's. So the claim is that the past does not matter. The past does not matter. Okay. And the transitions occur at discrete times. And we are already showing the discrete times here, n plus 1, n minus 1, n minus 2, all the way up to 0.2. So ये भी हम शो कर रहे हैं. और दूसरी प्रॉपर्टी इसको यूज करके हम क्या शो कर रहे हैं, इसको यूज करके हम शो कर रहे हैं कि दिस गाय शुड बी इक्वल टू xn plus 1 is equal to j given xn is equal to I. This is by using property 2. Using property 2. कि ये पास्ट को बिल्कुल भूल जाएं फिर. Given the present, forget about the past. Not only that, we are also saying that it is stationary. That means you go from n to n plus 1. This is the same thing as going from n plus 1 to n plus 2. Okay? And it's the same thing as going from 47 to 48. Same thing as going from 73 to 74. So this really is probability x1 is equal to j given x naught is equal to I. And we used Pij to denote this, which is the transition probability. In one time step, you move from state I to state j. What is the probability of that? That's the transition probability Pij. So that's the discrete time Markov chain. And we talked about the infinite state discrete time Markov chains. We talked about the classes of states, recurrent states and transient states, and irreducibility, where every state can communicate with every other state. So we looked at all of these probabilities and structures in the last few lectures. Now, today we are going to focus on the continuous time Markov chains, and it is no surprise that continuous time Markov chains are very similar to discrete time Markov chains. But there is a very important difference, and the important difference is that this property, out of these three properties, I'm going to keep the last two, and I'm going to relax the first. So Ctmc के लिए, you relax 1 and keep 2 and 3 as it is. Relax 1 to say what? That transitions can occur at any time. Transitions can occur at any time. Continuous time. ठीक है? So the definition of the Ctmc, we will give alternate definitions. The Ctmc is defined as a random process x of t with t greater than equal to 0. This is the definition of the Markov chain, continuous time Markov chain. Okay, a random process x of t greater than equal to 0, such that for all s and t greater than equal to 0, and for all I, j, and xu, which are all constants, So the definition of the Markov chain is, the Markov chain is defined as probability x of t plus s is equal to j given x of s is equal to I, comma, what is else is given is x of u is equal to small x of u, where u is greater than 0, of course, but smaller than s. U is smaller than s. So that means this is past and this is present. S is bigger than U, so S is more recent as compared to U. If X of S is given, then I don't need to worry about this X of U guy. So this would simply be equal to probability of X of T plus S is taking a value of J given X of S is equal to I, which, as we mentioned above, is the same as X of T is equal to J given X0 is equal to I. So what about the state space? The state space of Ctmc is still countable state space, countable state space. You can have infinite state space size, वो तो हमने discrete time Markov chain में भी किया था infinite states के साथ handle, but the state space would still be countable. What if they are not countable? If they are not countable, then you don't have a Markov chain. You will still have a Markov process, but it will not be a Markov chain. Will not be a Markov chain. Okay. So I'm going to give a couple of definitions. One is very important, is the holding time. Holding time. Remember, we said that in continuous time Markov chain, you can transition at any time, So what is the holding time? Okay, let tau I be the time the Ctmc or a Ctmc spends in state I, before transitioning to some other state. Okay, so that is tau I is the time Ctmc leaves state I, given that currently it is in state I. And this tau I, this is called the holding time in state I. So what does the Markov property tell us? Markov property tells us that probability tau I, which is a random variable, how much time do you spend in a state I, is greater than t plus s, given that this time is greater than s. According to the Markov property, this has to be equal to tau I greater than t. ये Markov property है ये, and Markov property तो Markov chain ने follow करनी ही करनी है, whether it is a discrete time Markov chain or continuous time Markov chain. So what this means, what this expression also means is that tau I is memoryless, and the only continuous random variable which is memoryless is an exponential random variable. Okay, so this implies that tau I is exponential with certain parameter lambda I. Okay. So with this in mind, it is important to realize that the time that you will spend in each state before you transition out of that state, it is going to be an exponential random variable. It is going to be an exponential random variable, which is a continuous random variable. Okay. तो एक स्टेट में जहां पे हम हर डिस्क्रीट टाइम के ऊपर ट्रांजिशन कर देते थे, n is equal to 1, फिर n is equal to 2, फिर n is equal to 3. डिस्क्रीट टाइम के केस में यहाँ पे ट्रांजिशंस होती थी. कंटिन्यूअस टाइम के केस में you just transition whenever you want, and that time, that holding time in a state will be an exponentially distributed random variable. Okay. Very, very interesting. Exponential के अलावा और कोई नहीं होगा. कोई और होगा तो मार्कऑफ प्रॉपर्टी चली जाएगी, मार्कऑफ चेन ही नहीं रहेगी, कुछ और चेन बन जाएगी बट मार्कऑफ चेन नहीं रहेगी. So if the chain has to be Markov, then the holding times have to be exponential, Okay. With this in mind, I have two views of continuous time Markov chains. There are two views of continuous time Markov chain. So view one is the following. A continuous time Markov chain is a random process, such that number one, time spent in state I before transitioning, its holding time is exponential lambda I, where lambda I is the rate. Lambda I is the rate of the exponential random variable, So व्यू वन में एक तो ये चीज हो गई कि एक स्टेट में जो आपने टाइम स्पेंड करना है वो एक्सपोनेंशियल होगा. एंड द अदर थिंग व्हिच इज essential in view one is that when Markov chain leaves state I, it enters some other state. It will leave state I after the holding time. The holding time पूरा हुआ वो लीव कर जाएगा. एक randomly amount time था जो exponentially distributed था with some parameter lambda I. So once it leaves state I, when the timer expires, it enters some other state. In some other state, state J, it enters state J with some probability, which is the transition probability going from I to J. Okay. It enters the state J with some probability Pij that is independent of the time spent in state I. So that's one view of Ctmc. Okay, times are exponential, holding times exponential, and number two, you have probability transitions governed by some probability distributions. Okay. This tells me that you can figure out an underlying what we call a jump chain. ये एक discrete time Markov chain है, ठीक है, जो उस continuous time Markov chain को represent कर रही है. This is part of that. It's a component of that. It's called the jump chain. Plus you have these holding times. So Ctmc is really same as dTmc plus holding times. dTmc जिसको हम कहते हैं कि ये जंप चेन है. हर कंटिन्यूस टाइम के अंदर एक ये जंप चेन छुपी होगी. Okay. Once again, this is the only one view. There is a second view of looking at the continuous time Markov chain as well. And the second view is let xij is exponential lambda I Pij. Lambda I Pij. So let's say that this represents the time to transition from state I to state J. State I से state J में transition करने की इतने टाइम के अंदर आप ट्रांजिशन कर देंगे स्टेट I से स्टेट J. Remember, if you are going from state I to state K, then it would be XIK. And that is both defined by the rate, कि उसमें आपने holding time कितना है, and also the probability that you will actually go to state J and not some other state K. ठीक है? So Xij, we define Xij to be those exponential random variable which represent the time to transition from state I to state J, specific state J. Okay. Then to state J where J is obviously not equal to I. और किसी दूसरी जगह पे जाना ही जाना है. ठीक है. So also let tau I is minimum of all of those times, min over j of Xij. हर वैल्यू ऑफ j के लिए I नोड I में आप बैठे हैं यहाँ पे, this is state I, and then you have many different states, 1, 2, 3 ... ठीक है. So Xij represents the time to transform from I to this K or J, जो भी आप कह लें इसको. ठीक है. So let's say tau I is defined as the minimum of all of those random variables. So let's say if you are going from state 1 to state 2 and state 3 and state 4, ये 4 आपके पास possibilities हैं. तो 1 से 2 तक जाने के लिए जो टाइम चाहिए होगा वो x12 है. 1 से 3 तक जाने के लिए x13, 1 से 4 तक जाने के लिए x14. टेक द मिनिमम ऑफ दोज. यूं समझ लें कि मैंने जितने भी आउटगोइंग एजेस हैं उनके लिए मैंने एक टाइमर रन कर दिया है. जो टाइमर सबसे पहले एक्सपायर होगा, मिनिमम ऑफ जे, जो टाइमर सबसे पहले एक्सपायर होगा, आई विल जस्ट मूव टू दैट स्टेट. ठीक है. इन अदर वर्ड्स, think about that you have 3 telephone lines coming in. These 3 telephone lines coming in. All of these 3 telephone lines, you are waiting for the ring to occur, and the waiting time is an exponentially distributed independently on each of the 3 telephone sets. Okay. Whichever telephone set rings first, so that means you have selected that state, you move to that state. Yeah. So let's say M is the minimum over J Xij. इसका जो आर्ग्यूमेंट है वो M है. That is what we are saying here is Xim is equal to the minimum time from Xij. ये इसका minimum time है. Okay. So view 2 is very different from view 1. View 1, but the claim is that view 2 leads to view 1. And vice versa can also be shown, but view 2 leads to view 1. And I'm not going to have a rigorous proof, but I'm going to have a very simple, explanation. Simple explanation. देखिए व्यू 1 में क्या चीजें थी. व्यू 1 में 2 चीजें थी. एक तो ये कि आपका होल्डिंग टाइम एक्सपोनेंशियल है, और दूसरा probability of transitioning from state I to state J governed by the same as discrete time Markov chain. So explanation अब इसकी. If सबसे पहले ये देखें कि if T1 is exponential lambda 1 and T2 is exponential lambda 2, then we can easily show that min of T1, T2, इन दोनों में से जो छोटा होगा वो भी एक एक्सपोनेंशियल होगा. वो भी ये हमने कहीं बहुत टाइम पहले किसी होमवर्क में भी शो किया था, lambda 1 plus lambda 2. This would be an exponential with lambda 1 and lambda 2. And the probability that T1 is the minimum of these two guys. T1 is the minimum of these two guys. What is the probability that T1 is the minimum of these two guys? Is lambda 1 over lambda 1 plus lambda 2. What would be the probability that T2 is the minimum of these two guys? That would be lambda 2 over lambda 1 plus lambda 2. These are the equations that we had proved in maybe 6 weeks ago, 4 weeks ago, 6 weeks ago. ठीक है, जहां पे हमने एक्सपोनेंशियल डिस्ट्रीब्यूशन एंड पोसॉन डिस्ट्रीब्यूशन एंड पोसॉन प्रोसेस पढ़े, वहां पे हमने कहीं शो किया. सो ये तो अब साइड नोट है, ये तो साइड नोट है. अभी हमने हमारी वो एक्सप्लेनेशन तो आई नहीं कि व्यू 2 लीड्स टू व्यू 1. व्यू 2 में आपने टाइमर चलाए हुए हैं, जो टाइमर सबसे पहले एक्सपायर होगा उस स्टेट की तरफ चले जाएंगे. ठीक है, व्यू 1 में you have these holding times and you have these transition probabilities. ठीक है, so सबसे पहले holding time. So holding time from view 2. व्यू 2 से होल्डिंग टाइम को देखने कैसे होगा. तो I is min of j xij, where xij is exponential lambda I pij. Okay, that means कि tau I जो minimum of all of these guys है, which are all exponential. So बहुत सारे exponential का अगर min लेते हैं तो you have an exponential. You still have an exponential. So that means T1, Ti would be an exponential with what parameters? Lambda 1 plus lambda 2. But यहाँ पे दो नहीं है, दो से ज्यादा भी हो सकते हैं. So you have summation over all j lambda I pij. pij. Okay. लेकिन व्यू 1 तो ये नहीं कहता था. व्यू 1 तो कहता था कि ये एक्सपोनेंशियल लैम्डा I है. So let's take a look. If you think about it, this lambda I can be pulled out of the summation because summation तो j के ऊपर है. ठीक है, so this is really equal to lambda I summation upon j pij. Okay, and what is this guy? This is one row of probability transition matrix, and sum should be equal to 1. Sum should be equal to 1. So this is lambda I. So that means tau I is distributed exponentially with parameter lambda I. ये तो हमने शो कर दिया कि holding time जो है from view 2 is the same as in view 1. ये view 1 के अंदर भी ऐसे ही था. The second thing that we want to show from view 2 is the transitions. So what is the probability that you transition from state I to state M is the probability that you transition from state I to state M is ये कैसे निकालेंगे? We are looking at the probability that xm is the min over all j xij. एक खास m है, वो आपका मिनिमम है. ठीक है, बिल्कुल उसी तरह से जैसे हमने यहाँ पे कहा था कि what is the probability that t1 is the minimum of t1 and t2, both are exponential. So this was simply lambda 1 over lambda 1 plus lambda 2. Okay. So this would, generalizing, this would be lambda I PIM divided by summation upon J lambda I Pij. And this really is, this again, this guy is independent of J, pulls out, okay? This pulls out and gets cancelled with this guy. Okay? And then you are left with summation upon all J Pij, which is 1. So all you are left is PIM, which obviously is the transition probability going from I to M. Okay, so this is also the same as view 1. So view 2 and view 1, they aren't really different, but very different ways of looking at it. So I'm going to give some example here. And the example is, we have talked about the state transition diagrams, probability transition diagrams. Okay, so I'm going to use a slightly different kind of a diagram. So consider a queue. This could be a bank, PDC counter, where there is a server. So this guy is server, and there is a queue here, and customers coming in one after the other. So there is some arrival rate, there is some service rate. So lambda, which is the arrival rate, is, let's say, 3 jobs or 3 customers per second. Okay. And the service is mu is equal to 5 jobs a second. Okay. You can well imagine that if mu is smaller than lambda, then the Q will increase indefinitely. We did this in the case of discrete time, continuous time ki case maybe. If mu is smaller than or equal to lambda, then the Q will increase indefinitely. Okay. So I can draw the state transition diagrams for this guy as well, showing the number of customers in the queue or number of jobs in the queue. You can have 0 jobs, or you can have 1 job, or you can have 2 jobs, or you can have 3 jobs, and so on and so forth, all the way up to infinity. If you are 0, then you have jobs, 3 jobs per second arriving. So there is some arrival rate here. This is not the probability. This is not the probability. This is the arrival rate. And this is the departure rate, mu. Okay. So this is lambda, and this is mu. This is lambda. तो जैसे जैसे देखिए कि जैसे जैसे आपकी अराइवल्स होती जाती हैं, जैसे जैसे अराइवल्स होती जाती हैं, आपकी क्यू का साइज जो है वो देखें लैम्डा के हिसाब से बढ़ता जाता है, और जैसे जैसे सर्विस होती जाती है वैसे वैसे आपकी क्यू का साइज छोटा होता जाता है. So let XA is the time to next arrival. Time to next arrival. Okay, and this is actually exponential lambda. If it is exponential lambda, it would have a mean value of 1 over lambda. Let's also assume that XD is the time to next departure. Next departure. And XA and XD are independent random variables. Okay. Time until something happens. Something happens. And this something includes arrival or departure. Arrival or departure. Okay. This time, tau I is actually going to be an exponential with parameters lambda plus mu. So देखें, suppose you are in state 2. Suppose you are in state 2. तो यहाँ पे देखें arrivals भी हो रही हैं, which will push you to state 3, और departures भी हो रही हैं, which will push you to state 1. So you will transition out of state 2. You will transition out of state 2 either by if something departs or something arrives. Something departs or something arrives. Okay. या arrival हो जाए या departure हो जाए, then you will transition out of state 2. Transition out of state 2. Okay. So दोनों में से जो भी पहले हो गया, minimum of arrival time, next arrival time, and minimum of next departure time. So XA और XD का जो min है वो हम निकालेंगे, और चूंकि वो both of them are exponential lambda and exponential mu, so this is exponential mu. Okay. So the min of these two guys will put you out of state 2, will put you out of state 2 into some other state, either 3 or 1, depending upon कि वो arrival थी या departure थी. But जो भी है उनमें से जो minimum होगा वो मुझे किसी दूसरी state में ले जाएगा. ठीक है? If it's the minimum, then the holding time will still be exponential of lambda plus mu. Lambda plus mu. So lambda I would be equal to lambda plus mu. Okay. So now question is the probability that on leaving state I, you will go to state I plus 1 and not to I minus 1, and not to state I minus 1. What is this probability? What is this probability? And this probability is really arrival is time is less than departure time. Only then you will move from state I to state I plus 1. एक arrival और आ गया आपके पास, ठीक है? And this would be equal to, once again, two events waiting to happen together in race with each other, and the events are independent, then the probability of each of these guys, you can see okay, this would be equal to, ये चीज भी हमने पहले सॉल्व की है. Okay. So now components of Ctmc, components of continuous time Markov chain. So हमने जैसे इसमें बताया था कि continuous time Markov chain consists of jump chain and the holding times. So holding times, and number 2, the jump chain. Or sometimes it is also called as embedded chain, which is a DTMC, और उसको पूरी DTMC की थ्योरी हम लगा सकते हैं. So how do you solve the Ctmc? Solving Ctmc for, let's say, for stationary distribution or limiting distribution. By the way, for the continuous time Markov chain, the limiting distribution, if it exists, and it will exist under very mild conditions, so if it exists, it would be the same as the stationary distribution. So in order to talk about it, I'm going to define Pijt, capital Pijt. This is the probability that at time t plus s, you are in state J, given that x of s is equal to I. So in ये देखेंगे x of s है, ये x of t plus s है. So time difference दोनों के बीच में कितना है? t units का, and that t units is here. So in t units you transition from state I to state j. Transition from state I to state j. I define this to be equal to probable Pijt, capital Pijt. Okay, and then you can see that Pijt is dependent upon I and j. ये दोनों पे डिपेंड कर रहा है किस स्टेट से ओरिजिनेट हुए हैं और किस स्टेट के ऊपर आपने टर्मिनेट होना है. ठीक है, बट आई एम इंटरेस्टेड इन phi j, the limiting distribution, उसका jth component, which is limit t going to infinity Pijt. Okay, now this guy is only dependent upon j. This is independent of I. तो ये वो ऐसी बात है कि आपकी जो probability transition matrix है, when you run it for a sufficient period of time, leave it there for sufficient period of time, then all the rows will become the same. So that's why it is independent of I. That's why independent of I. Okay. और Pijt हमने ये define भी कर दिया. So there's some notes here and you can verify these. And these notes are Pii0. अपने आप से अपने आप में जाना है at t is equal to 0. This probability is 1 because you are already there. You start from there. And Pij at 0 is equal to 0. ये 0 होगा for all I not equal to j. We can show that P of s plus t is equal to P of s P of t, where capital P I J T is the ith row, jth column element of a matrix PT, which basically contains Pijts. So P of t is equal to P11t, P12t, P21t, P22t, and so on and so forth. You can see that P of 0, what is this guy? This question, what is this guy? यह भी हमने बताया कि Pii0 जो है ये 1 होगा और Pij0 जो है ये हमेशा 0 होगा. So this would be simply an identity matrix. This would be an identity matrix. Okay, so we are going to take a look at a couple of examples. एक दो examples देखते हैं. And the first example is a very simple one. It's a very simple one. So let's say you have a continuous time Markov chain with two states. Okay, And let's say you have these two state Ctmc, state 0 and state 1. ये उनके बीच में चलती रहती है, state 0 state 1. Okay, so assume that the holding time, let's say lambda 0 is equal to lambda 1 is equal to lambda, which what that means is that the time that you will hold in state 0 is exponential lambda, and the time you will hold in state 1, holding time for state 1, is also exponential lambda, Okay, ये दोनों exponential lambda है. And the chain is toggling between these two states, and the chain toggles between these two states. ये बड़ी बोर किस्म की चेन है जिसमें 0 से 1 है, थोड़ी देर के बाद ये इधर चले जाते हैं, इधर चले जाते हैं. If this was a discrete time chain, तो ये तो बिल्कुल ही बोर होती. क्यों? एक टाइम स्टेप पे 0 से 1 चले जाएंगे, अगले टाइम स्टेप पे 1 से 0 वापस, फिर 0 से 1, फिर 1 से 0. So every time step you are moving from one state to the other state. This is a periodic chain. Periodic Markov chain. Okay, and not very interesting from a properties point of view. However, just to highlight the difference between the discrete time Markov chain and continuous time Markov chain, we are just using this Markov chain, जिसके अंदर holding times जो हैं वो अब आपके पास random variables हैं. Now you are not jumping every so often. Okay. So first of all, we have drawn the state diagram. What is the jump chain matrix? So this is the jump chain. And this would be jump chain when we have probabilities written here. And the probability transition matrix for the jump chain is 0, 0, 1, 1. Okay, this is the transition matrix for the jump chain. Transition matrix for the jump chain. So what are the probabilities associated with these two guys? So this probability is going to be 1, and this probability is also going to be 1. Why? क्योंकि sum of the outgoing probability is 1 होनी चाहिए. State 0 से एक ही outgoing जा रहा है, so उसकी probability 1 होनी चाहिए, and so is the case with state 1. Okay. You can find the probability transition matrix for the Ctmc. We can find PT here, and PT is capital P11 T, or in this case 00 T. Okay, and then 01 T, P10 T, and P11 T. Okay, you can find each of these guys by using the definition P00T, P01T, and so on and so forth. Okay? ये सारे हम find out कर सकते हैं. So P00T, एक example आपको दे देते हैं. P00T is the probability that x of t is equal to 0, given that x of 0 is equal to 0. Okay, and when does that happen? देखें, x of 0 is 0 and x of t is also 0. इसका मतलब ये है कि between 0 and t, there are even number of arrivals. हर अराइवल के ऊपर जो ये स्टेट चेंज हो जाती है, ये आपके जो अराइवल्स एंड अराइवल्स इज रियली कि कितनी बार आपके एक्सपोनेंशियल का टाइमर एक्सपायर हो रहा है, कितनी बार एक्सपोनेंशियल का टाइमर एक्सपायर हो रहा है। एंड द एक्सपोनेंशियल का टाइमर एक्सपायर का मतलब ये है कि पोसॉन अराइवल्स, दैट्स व्हाई we use this word arrivals. So remember that when you have Poisson arrivals, the inter-arrival time was exponential. तो यहाँ पे बिल्कुल exactly वही हो रहा है, exactly वही होगा. So we can find the probability of an even number of arrivals governed by Poisson distribution. And you can write these probabilities, all of these probabilities, by using the Poisson probability formula, and you will see that this turns out to be equal to 1/2 plus 1/2 e to the minus 2 lambda t. Okay. And this entire matrix for the Ctmc, this is not the matrix for jump chain. जंप चेन की तो वो ऐसी होगी जैसे डिस्क्रीट टाइम मार्कव चेन की हमने पहले देखी, ठीक है, बट नाउ दीज विल बी टाइम बाउंड, ये इनकी अंदर टाइम की कोई लिमिट्स होंगी, ठीक है. सो योर p of t turns out to be equal to 1/2 plus 1/2 e to the minus 2 lambda t. Okay, and I'm going to use this copy function here. And the other quantities are going to be similar, not quite the same. And instead of a plus here and a plus here, I have a minus here, Now, यहाँ पे देखें, यहाँ पे हमने कहा था कि P of t is the probability transition matrix. So लिमिटिंग डिस्ट्रीब्यूशन मैंने कैसे निकालनी है, टाइम को हम इंफिनिटी पे ले जाते हैं, pij, it will give you pi j. Okay, so the stationary or limiting distribution, to find the stationary or limiting distribution, limit t going to infinity p of t, this will turn out to be 1/2 and this is the one row is giving you what we call limiting distribution, which is also the same as stationary distribution. So by taking t going to infinity, you have found कि इस वाली मैट्रिक्स की जो कन्वर्जेंस होती है वो इस जगह पे कन्वर्जेंस हो जाती है, t infinity पे जाके you have this limiting distribution which would be the same as stationary distribution. So alternate way of finding the stationary distribution is by finding the stationary distribution directly. Pi is equal to pi times p. Okay, so then pi will be stationary distribution. So pi को हम ले सकते हैं pi 0 and pi 1. This to be equal to pi 0, pi 1 multiplied by this matrix here. इन दोनों को मल्टीप्लाई कर रहे हैं. So I'm just going to do it this way. ठीक है? Now इसको सॉल्व करते हैं, इसको सॉल्व करें and also use pi 0 plus pi 1 to be equal to 1. इसको भी यूज करें और ये बाकी दोनों को भी यूज करें. Turns out that pi 0 is equal to pi 1 cannot be different than 1 by 2. ये अगर मेरे पास 1 by 2 limiting distribution 1 by 2 आ गई है तो stationary distribution भी मेरे पास 1 by 2 आएगी because the limiting distribution is the same as the stationary distribution. ठीक है? Now I'm going to indicate here that there is a stationary distribution associated with the discrete time Markov chain, which is embedded in the continuous time Markov chain. जो jump chain है आपकी, उस jump chain के साथ एक stationary distribution होगी. That stationary distribution is not the stationary distribution for the Ctmc. Okay. So यहाँ पे मैं लिखता हूँ इसको. If a Ctmc has a jump chain, which is DTMC by the way, then the stationary distribution for the jump chain is not the same as the stationary distribution of Ctmc, and the reason is very clear. वो ये कि देखें स्टेशनरी डिस्ट्रीब्यूशन आपको क्या बताती है? स्टेशनरी डिस्ट्रीब्यूशन बताती है आपको what is the probability you are found in state 1, what is the probability you are found in state 2, what is the probability you are found in state j, and you are found in different states. तो वो probability distribution बता देती है आपको. ठीक है? वो fraction of time भी बता देती है, वो flow rate भी बता देती है. All of those things that we covered last time. Okay. But the question is कि अब हमारी transitions जो हैं वो बड़ी random times पे हो रही हैं. अब हमारी transitions are not happening nicely. 1 unit time के ऊपर नहीं हो रही. ठीक है? So see, transitions are happening not nicely at discrete times, but at random times. So किसी स्टेट में ट्रांजिशन जल्दी हो जाएगी, किसी स्टेट में ट्रांजिशन देर से होगी. भाई देखें, जिसका एक्सपोनेंशियल होल्ड टाइम कम होगा, the likelihood that you will find the Markov chain in that state वो diminish हो जाएगी. ठीक है? So let's say you have this Markov chain with state 1, 2 and 3, 1 से 2, 2 से 3, और कोई maybe आप इस तरह की कोई चेन बना सकते हैं. 1 से 3, 3 से 1, 1 से 2, 2 से 1, 3 से 2 और 2 से 3. ये फुल इस तरह की चेन है आपके पास. Now the problem is कि इसकी जो stationary distribution है, this is the jump chain. ठीक है? Now jump chain की यहाँ पे probabilities लिखी होंगी. If this is the jump chain, this will have a stationary distribution. If this is not the jump chain, then it will still have a stationary distribution. How do I find that stationary distribution? Okay. So think about it. कि you transition out from state 1. यहाँ पे आपने कुछ होल्ड करना है. अब डिस्क्रीट टाइम पे नहीं मूव करना, यहाँ पे होल्ड करना है. होल्डिंग टाइम के बाद आप बाहर चले जाएंगे. इफ दैट एक्सपोनेंशियल रैंडम वेरिएबल टर्न्स आउट टू बी वेरी वेरी स्मॉल, तो इसका मतलब है कि द लाइक्लीहुड ऑफ बीइंग इन स्टेट 1 विल रिड्यूस. ठीक है? एंड that is exactly why the holding times matter a lot for defining the stationary distribution of CTMC. इस CTMC की जो स्टेशनरी डिस्ट्रीब्यूशन है उसके लिए हमें होल्डिंग टाइम चाहिए होगा. होल्डिंग टाइम अगर थोड़ा होगा तो मुझे उसकी प्रोबेबिलिटी कम करनी पड़ेगी. होल्डिंग टाइम अगर सब का बराबर है तो जो जंप चेन की स्टेशनरी डिस्ट्रीब्यूशन है वही आपके CTMC की डिस्ट्रीब्यूशन है, उसी की स्टेशनरी डिस्ट्रीब्यूशन. ठीक है. So now there is very nice theorem here, and this makes complete logical sense, and this is that pi tilde, which is equal to a vector pi tilde, which is equal to pi naught tilde, pi 1 tilde, pi 2 tilde, and so on and so forth. Okay? So let's say this is the stationary distribution of jump chain. Stationary distribution of jump chain. This is the stationary distribution of jump chain. Okay. Let lambda i's are the rates of holding times. वो exponential distributions हैं, उनका parameter lambda चाहिए होता है, वो हमने निकाल दिया lambda I, वो assume कर लिया कि lambda I is. Then what is the stationary distribution of the CTMC? CTMC की stationary distribution क्या होगी? CTMC की stationary distribution बड़ा easily find out कर सकते हैं कि pi j would be equal to limit t going to infinity probability x of t is equal to j given x0 is equal to I, and this will be equal to normally this would have been pi j divided by sum of all the pi's. Okay, pi j would be equal to pi j divided by sum of all the pi's. But now we don't have pi j's. वो तो हम find out कर रहे हैं. We have pi j tilde. Okay, pi j tilde, and then you have summation upon all k, an element of the state space, pi k tilde. Vikas, you have a question? Vikas, आपका question? I guess not.
No, sir. No, sir.
Okay, so can you please mute? Thank you. Okay,
Sir,
so
yes.
so normally this would have been the case. This would have, ये सारे का सम जो है ये आपके पास 1 आना चाहिए था और ये आपके पास यही वाली चीज आ जाती, लेकिन ये जो टिल्डे हैं ये CTMC की स्टेशनरी डिस्ट्रीब्यूशन नहीं है, ये तो CTMC की नहीं है, ये तो उसकी जंप चेन की डिस्ट्रीब्यूशन है, जंप चेन की डिस्ट्रीब्यूशन है. सो इनको हमें वे करना पड़ेगा. किस तरह वे करना पड़ेगा? हमने इसको वे कर देना है. किससे वे करेंगे? वे कर देंगे लैम्डास से, इनके लैम्डास से वे कर देंगे. सो इसको लैम्डा जे से वे करेंगे और इसको लैम्डा के से वे करेंगे. एंड द रीजन फॉर दैट इज कि अगर किसी का होल्डिंग टाइम जो है वो ज्यादा है, किसी का होल्डिंग टाइम अगर ज्यादा है तो इसका मतलब है कि probability that I will find that the CTMC in that state is going to be longer. DTMC में ऐसा नहीं होता. DTMC में तो जंपें आपकी जो है वो डिस्क्रीट टाइम पे लग रही होती है. ओके, तो इसलिए CTMC में जो स्टेशनरी डिस्ट्रीब्यूशन है is also dependent upon these lambdas. Also dependent upon these lambdas. Yeah. So there's a couple of examples. ये दी गई हैं. I'm going to very quickly talk about what we call the generator matrix. Generator matrix. Generator matrix. ये भी स्टेशनरी डिस्ट्रीब्यूशन फाइंड आउट करने के लिए इस्तेमाल होती है. देखें, हमने दो तरीके तो पहले देख लिए थे. पहला तरीका ये था कि टेक टी गोइंग टू इंफिनिटी. Take time going to infinity, you will see the limiting distribution, which will be the same as the stationary distribution. The other method was to find the stationary distribution directly. Okay? And the third method was कि ये आपने jump chain की stationary distribution find out की और उससे jump chain की stationary distribution से Ctmc की stationary distribution आप निकाल सकते हैं. So this is for jump chain. And this is for Ctmc. Okay. Now I'm going to use this generator matrix notation. Generator matrix notation, जिसको use करके आप फिर stationary distribution निकाल सकते हैं. Use करके stationary distribution निकाल सकते हैं. Okay. So I'm going to define a generator matrix. ये आपके पास एक matrix होगी इस तरह की, जिसमें I rows and j columns, बिल्कुल उसी तरह से जैसे probability transition matrix की होती है. I rows and j columns. Okay. So इसके अंदर I will pick Gij, ith row and jth column का जो element है, this would be equal to lambda I Pij, and Pij is the transition probability from jump chain. Lambda I is the holding times, rates. Holding time की rates of holding times. उसको हम Gij से denote कर देते हैं. Gij से denote कर देते हैं. When I is not equal to j. What if I is equal to j? Okay. So basically I am looking to find Gii. ये हमने find out करना है. I find out this Gii. Choose Gii such that इसकी जो पूरी रो है, इसका sum जो है वो 0 हो जाता है. Such that summation upon j, Gij is equal to 0. ठीक है. So इसमें से मैं I वाली टर्म निकाल लेता हूं. So Gii को मैं निकाल लेता हूं. So Gii plus summation upon j not equal to I, Gij is equal to 0. So इससे मेरे पास आ जाती है Gii is equal to negative of summation j not equal to I, Gij. But Gij is equal to j not equal to I. Gij जो हमने define किया है is lambda I Pij. Lambda I Pij. So this would be equal to minus lambda I. The rest of this guy, this either adds up to 1 or is 0, or lambda I is 0. Okay. So आपके पास ये generator matrix एक आ गई है. So generator matrix G has elements Gij, such that Gij is equal to lambda I Pij if I not equal to j. And if I is equal to j, this is simply equal to lambda I if I is equal to j. Okay. So I'm going to make some statements without proofs, without the proofs. One is that the derivative of the probability transition matrix for the Ctmc, P of t is the transition matrix for Ctmc is equal to, ये आपके पास एक differential equation बनती है, G times Pt. One is this, okay. P prime t is the derivative of Pt, and Pt is the probability transition matrix for Ctmc, not for the jump chain, for Ctmc. And Pt has elements capital P, I, J, T, function of time. Okay. So, example, I'll do two quick examples. So let's say you have a generator matrix, and the generator matrix given to you is minus lambda, 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 minus lambda. देखें इनका sum जो है वो हर रो का वो 0 हो रहा है. So दूसरी चीज जो हमने before I complete this example is कि stationary distribution times G is 0. We can prove this as well. And I will skip the proof. Okay. So I have to find the stationary distribution for this guy. And the stationary distribution for this guy is found by putting pi of G is equal to 0, which means if you have pi 1, pi 2, or if you call them pi 0 and pi 1, pi 0 and pi 1 times G, which is minus lambda, lambda, lambda minus lambda, this is equal to 0. So you get two equations here. You will get two equations here, but those equations will be redundant. So also use pi 0 plus pi 1 to be equal to 1. Okay. Solve, and you will get pi 0 is equal to pi 1 is equal to 1 over 2. 1 over 2. Sometimes we use the probability transition matrix, and sometimes we use G. Sometimes we use G to show what we call a probability transition rate diagram. A transition rate diagram. Transition rate diagram. These are equivalent diagrams. So हमने probability transition diagrams तो देखी हुई हैं, वो इस तरह की होती हैं आपके पास state 1, state 2, state 3, and there is some rate flowing between 1 and 2, 3, 1, 2, इस तरह कुछ चल रहा होता है, ठीक है. But on the edges you have the probabilities of transition, ठीक है. यहाँ पर transition rate diagram में what you have is G12, is G12. यहाँ पे G21, okay, and G32, etc., etc. And these can be of course greater than 1. Can be greater than 1. क्योंकि probabilities नहीं है ना, so these numbers can be greater than 1. ठीक है. So I think we are running out of time now. I have a couple of examples that I would like to finish maybe in the next class. The next lecture is going to be the last lecture, and yeah, we will finish the couple of examples. So next time we will do 2 examples of Ctmc and a little bit of queuing systems. Not too much in queuing systems. कुछ तो हमने चीजें पहले cover कर ली हैं. When we cover Ctmc, we will implicitly be covering queuing systems as well. Okay. So we will cover this next time. Today, I think I will close the session. If there are any questions, we'll be happy to answer before we close. Quick questions, eh? No questions. So I'm going to stop the share here and we'll end the session. We'll upload the video as soon as it is available.